Very well. So in this screencast, we move on from volumes of known cross-sections, volumes of solids with known cross-sections, to volumes of solids of revolution. So let's talk briefly about what we mean by that. This will establish our content. So you have some function. It's some function f of x. It's continuous on some interval from a to b. And what we want to do is we want to take the region that's bounded by f of x and the axis from a to b. We want to take that region and we want to revolve that region about the x-axis. So we take this region and we spin it around this pole here. So it becomes a three-dimensional solid, and that three-dimensional solid looks something like that. It's got a base and it's got a top, that kind of thing. Maybe it's a vase or a vase or whatever. So the question in this screencast is, what's the volume of that vase or that vase? What is the volume? And you may have guessed that what we do with this is we consider a representative rectangle that gets spun around this axis here. What happens when you take a rectangle and you spin it about a pole? Well, you get a tuna can, right? You get a tuna can. This rectangle spins around in 3 dimensions and it gives you a tuna can. What's the volume of a tuna can? Well, a tuna can is a circle with some depth. It's a circle with some depth. Well, what's the radius of the tuna can? Well, the radius of the tuna can is whatever this height was on the rectangle. So that's the function value. What's the thickness of the tuna can? Well, the thickness of the tuna can, this thickness, is whatever this distance was over here. That's a change in x. And that's true for this tuna can, or this tuna can, or this tuna can, or this tuna can. All the tuna cans are the same all the way across. You just have a vase that is made of tuna cans. And so when we go to find the volume of this solid, it's the integral from a to b of this pi function squared delta x becomes dx. This is the formula that calculus students have memorized for years for volumes of solids of revolution. Integral pi function squared dx. I will illustrate with a couple of brief examples. We imagine that you take the curve y equals square root of x from 0 to 4. You take this region and you revolve it about the x-axis. It makes some shape like this, and you're looking for the volume of that shape. But the volume of that shape is an integral of pi function squared dx. From where to where? From 0 to 4. The function is the square root of x. And so it becomes our job to decide how to do this. Well, square root of x squared is pretty easy. And so we think to ourselves, do we have an antiderivative for this? You bet we do. Substituting 0 will go easy, so we'll substitute 4, that's 16 over 2, 8 pi. That's the volume of the solid. One more. So in this case, we imagine that you have the curve y equals secant x. And this region is from 0 to pi over 3. It's this region that we're going to revolve about the x-axis. That's our job. And so what does that solid look like? Well, that solid, when it's revolved, looks like, well, it goes off the screen, but it looks something like a tree trunk, I imagine. And we're looking for the volume of that solid. How do you find the volume of that solid? Well, volume is an integral of pi times the function squared dx. From where to where? From 0 to pi over 3. Secant squared x. We know a function whose derivative is secant squared x. That's tangent x. We know that. So then all we have to do is know what the tangent of pi over 3 is, and then what the tangent of 0 is. We've got the volume of the solid. Each time, what's important? We recognize that each little representative rectangle that spins around that axis creates a tuna can. And the volume of a tuna can is pi r squared times the height. The r squared in these cases is just a function value. And then we do the stuff we remember from Calc 1, fundamental theorem, and we've got it. I will illustrate with some other examples in another screencast, but this is the basic idea for now.